Welcome to this web lecture on network flow problems. Today we're going to look into the example of TUI Airlines, which operates a network of direct flights within Europe, and they allow passengers to change over between flights. So for instance, in this network, if I would like to go from Rome, so FCO, to Brussels, I can simply change over in Zurich. This airline now has an issue because their direct flight from Rome to Amsterdam was cancelled, and passengers must be reassigned to different flights. Within this context, you can ask multiple different questions. So first of all, how many passengers can you reassign the most? How can you assign all passengers from the cancelled flight to minimize cost? And which passenger shall sit on which seat? Today, we're going to look into the second question. How can you assign all passengers from the cancelled flight to minimize cost? So what we would like to do in the so-called minimum cost network flow problem is we would like to send n items from a source to a sink in a way that costs are minimized. So for example, we would like to send 15 passengers through the airline's network from the source that is Rome to the sink that is Amsterdam. So for example, we could send them from Rome to Zurich to Brussels to Amsterdam if the capacities actually allow for that. So we would like to model the so-called network flow problem. So what we're doing is we're identifying sets and parameters, we're introducing decision variables, and we're formulating constraints and the objective function. First of all, which sets do we have to consider? We have to consider the set of airports, so Amsterdam, Brussels, Rome, London, Heathrow, Munich, Toulouse, Vienna, and Zurich. In a second step, we are identifying the parameters, which are the ARC capacity, UI, from an airport to another airport. And we, of course, also have to consider how many people we actually have to transport, so the n items, or the 15 passengers. And in this case, we're considering that as a origin demand, so as a supply, and as a destination demand, so as a demand, which is 15 in either case. And we're now particularly only considering that for Rome and for Amsterdam. And lastly, we have to consider the traveling costs, which are then, of course, directly linked with decision variables. So the number of people that actually travel from one airport to another airport. So for instance, from Toulouse to Zurich. In a second step, we're now formulating the constraints and the objective function. So the constraints that we have to consider, the first constraint is adhering to ARC capacity, which is fairly obvious. If we only have 10 spots left on a flight, we cannot send 11 people along this ARC. Then we have to consider supply and demand. So for example, if there's 10 people arriving in Rome, we need to have at least 25 people that leave Rome again, because otherwise we don't take enough people. While vice versa, in Amsterdam, if we have 25 people entering Amsterdam, only 10 people have to leave again. The next thing that we have to consider is flow balance. So the number of people that enter an airport also has to equal the number of people that leave this airport, obviously with the exception of Amsterdam and Rome. And lastly, we have to consider non-negativity of decision variables, because obviously we don't want -7 passengers on a flight. In the objective function, because we're considering the minimum cost network flow problem, we're simply minimizing the total costs. So the costs per ARC multiplied with the number of people that use this ARC. What are the differences to the maximum flow problem that we already considered before? So first of all, the objective function is different, which is fairly obvious. In one case, we would like to send as many people as possible. In the other case, we know how many people we have to transport, and we're trying to minimize cost. Another small change is that we do not have a no cycles constraint, so we don't restrict that there's 0 people entering Rome. And what I would like you to look into is why we can drop this constraint, or maybe even why we have to drop this constraint in certain circumstances. And now let's look into an extension of this case. So now we have passengers which receive food and drink on all flights. Due to supply issues at some airports, the airline must send groceries on their flight. So for example, Toulouse and Vienna don't have any groceries anymore, and you have to supply this from London Heathrow and from Amsterdam and from Rome. Also here we can ask multiple different questions. How much food can the airline send at most? How can you satisfy all food requirements at all airports at minimum cost? Or does it make sense to buy from other suppliers? Or how much do costs reduce if the airline deserves not to serve food on some flights? And we're now going to look into how can you satisfy all food requirements at all airports at minimum cost. And what we're doing here is we're actually just looking at this same mathematical model again. And we're going to do mild changes to this mathematical model, or to this definition of a mathematical model, such that it fits to the case of transporting these groceries on the flights. So the first thing that we have is we don't only have supply and demand at one node each, but we now have a set of nodes that might have supply or demand, which means that we have to define the supply and demand as parameters for every location that has this, and for this we're introducing sets, which are then subsets of the set of all airports. The next thing that we have to consider is, of course, meeting supply and demand also then has to hold for all origins and all destinations, not only for Rome and for Amsterdam. And then, of course, also in the flow balance constraint, we have to remove all origins and all destinations, not only Rome and Amsterdam. Other than that, we're actually looking at more or less the same mathematical model. What I would like you to take away from this introductory web lecture on the minimum cost network flow problem is, first of all, the problem formulation, both in the more specific case with only one origin and one destination, but also in the more general case with multiple origins and multiple destinations. What I would like you to look into is this dropped constraint and why we can drop this constraint. And lastly, what we're going to do in the next web lecture is we're going to look into multiple passenger types, which is not the same as shipping multiple different groceries throughout the network. Thank you very much.